Hello, I'm Yoon Young Cho. I have developed a two-axis cup gimbal stabilizer as part of final project for dynamics at Olin College of Engineering. I'd like to go through the system modeling, mathematical analysis of the dynamics of the system, control and simulation, and finally to hardware implementation and a proof of concept demonstration. Here we have the system model rendered in SolidWorks. The idea is that the payload, in which case we have coffee, is going to be held within that cup holder, and it is going to be controlled by the two motors in the pitch and roll directions. This is a diagram, in fact, an abstraction of the system model that you have just seen. It basically specified all the dimensions and the relationships between the frame coordinates that you're going to be referred to in the following sections. Here's a basic illustration of the translational relationships between the frames. As part of the preparation for the constrained dynamics of the manipulator system, in which case we have, well, two manipulators, which are the two motors. We are basically defining the coordinate systems with respect to the two generalized coordinate systems in which all of the positions and velocities are defined with respect to, well, in this case, two variables, which are pitch and roll. After we define the positions, we basically invoke the rate of change transfer theorem that is also illustrated above to basically get the child frame's velocity with respect to the reference frame, the velocities of the reference frame in terms of like linear and angular components, as well as the positional offset of the child frame from the reference frame. Afterwards, we simply take the Lagrangian of the system, where T is the kinetic energy. In this case, it's simply the combination of linear and angular kinetic energies. And V is the potential energy, in which case we just have the gravitational potential energy. The differentiation of the Lagrangian with respect to the omegas and the thetas, which are our generalized coordinate systems in terms of its position and velocity, gives us the equation of motion, where Q sub I is the external force, and the terms on the right will yield us the relationships between each of our state variables and external force upon the system. While solving for the differential equation yields us with these very messy equations that give us basically the formula for obtaining the angular acceleration components. It is not quite readable, but this is in fact what the system will behave with respect to its current state, given as the thetas and omegas, and the input given as the tau or the torque. Now that we have finished analyzing the system, we would like to consider a control solution that would stabilize the system, in which case we could simply consider a full state feedback controller in which we just have the state variables that are influencing the gain with respect to its deviation from the reference signal. Shown here are the basically what the plant will behave without being controlled. As you can see, the behavior is highly nonlinear and very turbulent. And afterwards, we basically show a naive implementation in which only the state variables are taken into account when determining the gain for the controller. Whereas the system response is not terrible, we do see a very drastic steady-state error, which makes the control not exactly desirable for this control scheme. And therefore, we introduce this absolute term, which is the sustained displacement from the reference point, which is effectively the integral term that corresponds to like a PID controller. This is in fact analogous to a PD controller for the former case, and in the latter case, PID controller, in which the introduction of the integral term effectively mitigates for the steady-state error. Here we see a MATLAB simulation that also displays the state of the cup over time. It initially starts at an offset of 20 and 30 degrees in terms of roll and pitch respectively, and over time you can see that just as we have seen in the step response, it returns to a stable state in which the orientation is orthogonal to the ground plane. Now that we have completed the mathematical discussion of the system, we will basically go over the hardware implementation of the system, basically how it was built in real life. Hello, so this is the fully assembled prototype cup stabilizing two-axis gimbal. As the name suggests, the whole intent of this device is to stabilize the cup's orientation such that it is going to maintain a level orientation to the ground at all times. Right now, obviously it has a cup, and as payload, we have water in it right now. But mostly, the inspiration from the project came from the desire to bring coffee around while walking in a turbulent manner without having to worry about spilling the coffee. So this is the entire device, and well, here we have the main processor, the Arduino Uno. I was kind of worried about its processing power, but it turned out to be okay in terms of how fast it's responded to external stimuli. We have the IMU, which is the main sensor for sensing our orientation. It is actually the 9 degrees of freedom IMU, which means that it has a 3-axis linear accelerometer, 3-axis angular velocity gyroscope, and a 3-axis magnetometer. And obviously, because we're trying to cancel out the effects of gravitational vectors, the magnetometer is not exactly as useful as the other two, since it only dictates your yaw direction as opposed to the pitch or roll. So if you consider yourself going forwards, so X is going forwards direction and Y is going the leftwards direction, and Z is going in the up direction. So like these are the three principal axes in the right-hand coordinate system, as like it is typical in a robotic environment. You would consider this the roll motor or the X motor, and you would consider this the Y motor or the pitch motor. And as a combination of the operation of these two motors, you can actually cancel out the effects of like your base coordinate orientation such that the instability in your base coordinate system will not affect the coordinate system of the cup or the frame of the cup, such that it is going to maintain stability over time, such that it is going to be parallel to the ground plane and orthogonal to the gravitational vector, which means that basically it is going to prevent from spilling the coffee. So the device is currently tethered. So this is the motor driver, dual 7 amps motor driver brushless, or brushed DC, I'm sorry. And it's currently getting power from a 5 volt 12 amps wall adapter. So like obviously it is tethered and it greatly undermines the mobility of the device. But considering that it would have taken a lot longer for the batteries to ship, it was a reasonable choice for the device to be tethered at this moment, as it was mostly intended to show how the device was intended to operate based on the mathematical analysis and the constructed system as a whole. Beginning demonstration of the two-axis gimbal for cup stabilizing.